So next we're going to talk about the methods used to mine frequent item sets. We're going to talk about a priori and FP growth, and E-collect is actually a very easy using a different data structure, vertical data format to support frequent text mining. It's very easy to understand and efficient. So as we mentioned earlier, a priori algorithm utilize the a priori property of frequent item patterns. Then what is a priori property? The a priori property says that for frequent item sets, any superset of a non-frequent item set cannot be frequent. Those are all very intuitive rules. So if beer and diaper is not frequent, then beer, diaper, nuts cannot be frequent, right? The second part of the a priori property is any non-empty subset of frequent item set must be frequent. If beer, diaper, nuts is frequent, then any combination of the items in the subset must also be frequent, right? So using this a priori properties that we can actually have, well, they have developed some scalable mining methods. All of those methods more or less used a priori property, but a priori get the name, the a priori method algorithm. So a priori is a candidate generation and a test approach. And overall, used the a priori properties to prune. Prune means remove. To remove any item set which cannot be frequent along the way of searching for longer and longer item sets. So the methods, first, the items are sorted alphabetically. This is the important step. It makes the following computation much easier to understand and also efficient. Initially, we need to scan the database once to get frequent one item set. So we'll find from the database all the unique items, and we find the frequency of those unique items. So this gives us frequent one item set. Then we start iteratively generate longer item sets. Every time from one item sets, we add one item to create two item sets. From two item sets, we add one item to create three item sets. And along the way, we check the support for those candidates that we have generated against the database to find the support. If the support does not meet the threshold, we can drop them. Because if a K item set is not frequent, then K plus one item set cannot be frequent, right? So we can just drop them. Then we terminate when there's no frequent item candidate set can be generated. That's the end of the entire process. And then we can collect all the frequent item sets. So the item sets that meet the threshold of variant length will all be output as frequent item set. Okay, so let's look at one example. So this is the transactional data from the all electronics branch that we have, 9 transactions and the list of the items. We used the 1, 2, 3 here as to mark the items, so it's easier. for us to see how the items will join and grow the length. So first we find the unique item set. So 5 unique items has been identified. Then we scan the database to find the count for each of the candidate. In this example, we set the minimum support to be 2. So we use the support count 2 as the threshold. So all of those 1 item set will be kept as the length 1 item set because they are all frequent. Okay. And then next we're going to grow those item sets by adding items to make length 2 item set. So we do a join of those items to find all different possible ways of combining 2 items. So here, because every individual items is frequent, so we actually keep all the possible 2 item set as candidate. If any of those are infrequent, then we don't need to check this, because remember, a priori property tells us if this is a frequent item set, then any of its subset should also be frequent, okay? Because we know that all of those 1 item set are frequent, so all those combinations going to be candidates, valid candidates, that we need to scan the DB database again to find the count for each candidate item set. So after we find that, we can see some of them does not meet the threshold, we remove them. Now our length 2 item set going to look like this. And we start to further grow the item sets. We join those item sets. How do we join those item sets? So the joinable item sets is defined because we already sorted the items alphabetically, remember? The joinable item sets are the item sets sharing the same prefix and differ only in the last item. So ABC and ABD are joinable because they share AB, only C and D are different. ABC and BCD cannot be joined because they don't share the same prefix, okay? So this is our joinable conditions. So coming back to our example, we can join item 1, item 2, item 1, item 3. This can be joined to become item 1, 2, 3. So if this is going to be frequent, then all its subsets going to be frequent. And we check item 1, 2 is frequent, item 2 and 3 is frequent, and item 1 and 3 is also frequent. And all the individual items are frequent, right? So therefore, this is a good candidate that we put it here. And we can also see that 1, 2, and 5 can be joined, right? These 2 records can be joined. And we check again to see if 2 and 5 are frequent. They are, okay? So this is our second good candidate. And then we can check and see that shared prefix, then 2, 3, 2, and 4, then 2, 3, 4 may be a good candidate. Is it good? Then we check 2, 3 is frequent, 2, 3, and 4 is not frequent. Therefore, 2, 3, 4 cannot be a candidate. Similarly, we check 2, 3, 5, 2, 4, 5. We found those are all not good candidates because subset of them are not frequent. If subset of those cannot be frequent, adding an element to it cannot make it frequent. Therefore, we don't need to generate those candidates. Only those are viable candidates. So 3 item candidates. We scan the database again to find the count, and we see they are still frequent. And from here, let's see, can we join them? One possible join is 1, 2, 3, 5. But 2, 3, 5 is not frequent, right? It's not in this table, so therefore it's not frequent. Therefore, we cannot grow the item set and still make them frequent. Any adding additional items will make them infrequent. Therefore, we stop here. So this is a priori algorithm. What we observed is there are lots of database scanning. The database needs to scan as many times as the maximum length of the frequent item set you're going to discover. Scanning database is a very costly process. Therefore, a priori is not very efficient when you actually have very dense database that this pruning process does not reduce the candidate by a lot, and you have to scan the database multiple times to find the counts for the long item sets. Okay, so we have described that. A question that I used to get from student is why the joinable condition is defined this way. Why cannot ABC and BCD be joined? So the idea is we don't have to join ABC and BCD because if this two generates a viable candidate, that candidate will be ABCD. If ABCD is viable, then ABD must be viable, must be frequent. If ABD were there already and we have ABC, we would already join them. Okay, so it's not necessary, it's not needed for the items who does not share the same prefix to join them, because since we have sorted items alphabetically, if an item is a viable candidate, we would not miss them. They should already be generated without joining those items who does not share the prefix. Okay. Those example of joins, I think we already covered all of that. So we mentioned that scanning database is a very costly process. See, every step we need to scan. And that is also a place that can be optimized. To make the count process more efficient, a data structure called hash tree is being developed. A hash tree has a tree structure, and every node performs hashing function. So in each iteration, every iteration we basically need to get the count of some candidate item set, whether it's 1 item, 2 item, k item set, we need to find the counts. Hash tree supports counting by making every candidate walk the hash tree. They traverse the tree to find matches, to identify the candidate that appears in each transaction. So we have the hash tree was built using the candidate item sets, okay? And then each transaction, in each iteration, every transaction need to walk this hash tree. If a transaction match one item set in the tree, that item set going to have a count increased by 1. Okay, so after each transaction walked this tree, then we know how many candidate item sets match this transaction and got their counts updated. So we do that for every iteration of varied length of the item set. So this is a relatively efficient way to generate counts for a priori algorithm when the algorithm needs to scan database a lot of times to find the counts. Okay, I think I'm going to stop